All right, welcome everyone to GOCC once again. And today we have the pleasure of having my co-advisor, Ben Braun, not my primary advisor, but also helps me out a lot. So really looking forward to him talking to us today about lattice polytopes. But before I let him begin, I would like to remind us of our community statement, which is that we're all learning, including the speaker and the experts. We're all learning here, and everyone has something to contribute. So if you have comments that might be helpful, please let us know in the chat, or you can interrupt if the speaker's okay with that. And also, no one has all the answers, so it's okay if people don't know answers to questions. And so hopefully this is a welcoming, open environment where we can all feel free to engage and learn together. So with that said, I would like to welcome Benjamin Braun from the University of Kentucky. So Ben, take it away, please.
All right, awesome. And you all, Matthias, you can see my my OneNote file here, right?
Yes, looks good.
Okay, awesome. Okay, I'll try to keep an eye on the chat, but if a question gets put in there and I miss it, then please just interrupt me and ask. So, all right, yeah. So the purpose of this talk is definitely to be kind of a introductory survey, and so hopefully there will be a few good tidbits of information for people, even the experts in the Zoom room, but it's definitely intended to be inviting. So if there's anything that doesn't make sense, let me know. I'm certainly sweeping a lot of details under the rug for time reasons, but I'm happy to kind of talk about them if needed during the talk. And I don't have any, I'm not worried about getting through all the material. I'm just going to kind of talk until either time runs out or I'm done. So, okay, so first of all, if we're going to talk about lattice polytopes, which is what I want to talk about, we need to talk about convex hulls. And so the definition of a convex hull is if you have n points in R to the D, so that's P1 through Pn in R to the D, the convex hull of P1 through Pn is given by the set of all linear combinations, sum of lambda IPI, where we have non-negative coefficients, real coefficients, and the sum is equal to 1. And so you can derive this in a very natural way by kind of thinking about affine geometry. But kind of for our purposes, I'll just illustrate that if you have 2 points, then if you take all the linear combinations of this type, what you get is lambda P1 plus 1 minus lambda P2, where lambda runs between 0 and 1. And that exactly parameterizes the line segment between P1 and P2. So you can think of the convex hull as being all of the points, the whole space that's kind of inside of P1 through Pn, but in this linear way. So all the kind of quote unquote sides of the polytope are going to be flat. They're coming from hyperplanes. And so the way that we define a lattice polytope is that we restrict the points defining this convex hull to be integer vectors. So a lattice polytope, which I might often say an integer polytope, lattice and integer for me are kind of interchangeable terms, is P equal to the convex hull of V1 through Vn for V1 through Vn in Z to the D. And this is called the vertex description of the polytope, or the V description. And the dimension of the polytope is the dimension of its affine span. So if you don't know what that is, don't worry about it. That's something you can look up. The point is that there's some smallest affine linear subspace that contains it. For example, for 2 points, the smallest affine linear subspace containing them is the line through that point. So that's a one-dimensional polytope, even if P1 and P2 in this example up above are in a very high dimensional space. And so what I want to do here is now I just want to give a bunch of examples, okay? Because I think examples really are how we make sense of everything. That's actually a very precise statement, kind of coming from cognitive psychology of how people learn math. But the notation I'm going to use is E sub j is the jth standard basis vector in R to the n. Okay. So first of all, the first lattice polytope you should know is the standard simplex, usually denoted as sub d. And that's the convex hull of the standard basis vectors E1 through ED and the origin. And so in R2, it's just E1, E2, and the origin, you get a little triangle. In R3, you get this tetrahedron. It's not a regular tetrahedron, right? But you can see it's just like this little corner with the origin and the standard basis vectors. And the reason why the standard simplex is important is that it has minimal volume among all lattice simplices. And I should say a simplex, I'll define this later, but a simplex is a d-dimensional lattice polytope with d plus 1 vertices. So it's kind of like the least number of vertices you need to define something d-dimensional. So it's triangles in R2, tetrahedron in R3, etc. And this condition that we have integer points as the vertex set, the V description, says that, like we can't continue to kind of subdivide this farther. There's some limit to how small things can get if all the corners are going to be integer points. All right. As a second example, we have cyclic polytopes. And so for two parameters n and d, the cyclic polytope, C and d, is the convex hull of the following points. So what you do is you take the curve in R to the d, where the coordinates are x, x squared, x cubed, x to the fourth, up to x to the d. That's called the moment curve. And you evaluate x equals 1, 2, 3, 4, up to n. That gives you n points on this algebraic curve in the space. You take the convex hull. So for example, here is the two-dimensional cyclic polytope with 4 vertices. So I have the point x comma x squared. So this is the point 1, 1, 2, 4, 3, 9, and 4, 16. And if I take the convex hull of those 4 points, I get this kind of skinny foregon. Right? And the reason why cyclic polytopes are of interest is because they have a lot of very important extremal properties. This curve, the moment curve, places these points in very general position. And so somehow it's extremal in many regards. All right, so another pair of examples, they really do come as a pair. One is the -1, 1 cube, denoted -1, 1 to the d. This is the convex hull of all plus minus 1 vectors in R to the d. So in R2, you just take 1, 1, -1, -1, 1, -1, and -1, 1. You take the convex hull, you get this square. And then there's also the d cross polytope, diamond sub d. That's the convex hull of all the standard basis vectors and their negatives from 1 to d. So in R2, you can see we have E1 and minus E1, E2 and minus E2. In R3, we have E1 minus E1, E2 minus E2, and E3 minus E3. Notice that the origin is inside that three-dimensional picture, though I didn't draw it to kind of muddy it up. But the cross polytopes and the -1, 1 cubes do contain the origin in their interior. And one of the reasons why these two polytopes are of interesting, is that first of all, they have a lot of symmetry. They've got type B Coxeter symmetry. And so the -1, 1 cube in particular shows up a lot in various kind of type B Coxeter settings. But from a geometric perspective, these form what's called a reflexive pair. So there's a notion of geometric duality for polytopes. And these are a pair of lattice polytopes, which are geometric duals of each other. So in response to the chat, the convex hull of just the vectors E1 through ED is also called the standard simplex, because technically, if you take the lattice contained in the affine span of the standard basis vectors, then the convex hull of E1 through ED is a minimal volume lattice simplex in that lattice. It's a different looking lattice, but the convex hull of E1 through ED is a d-1 dimensional polytope, and in its affine span, it actually is a standard simplex up to a unimodular transformation. Yep. Okay, cool. So this is a reflexive pair. I'll talk more about reflexives in a little bit. All right. Another example is a rectangular simplex. So if you have d positive integers and 1 through nd, you can take the convex hull of the origin and then ni times ei. So you scale the standard basis vector by ni for each I equals 1 through d. So for example, S2, 5, you've got the origin twice E1 and 5 times E2, and you take the convex hull and you get a simplex that's scaled independently in each dimension, or in each coordinate, if you like. And these actually are surprisingly complicated algebraically and have interesting arithmetic properties. So one thing I want to point out about the examples so far is that these examples have a number of different sources. You know, the standard simplex really is about kind of the geometry of the lattice. It's like the smallest thing you can get. And the cyclic polytopes really come from like asking, can we put points in really general position? And we do that through, you know, this moment curve, which is an algebraic construction. And the cubes and cross polytopes, somehow, if you have one, the other arises through duality. But also these kind of come up in a natural way if you're thinking about symmetry groups. And the rectangular simplex really, its properties are controlled by a lot of number theory, right? And so, so there's a lot of arithmetic involved in the study of lattice simplices. But they also are very common in combinatorics, especially enumerative combinatorics, because of their connections with different combinatorial objects. So let me give you 3 examples of this. There's tons of examples. But one example is order polytopes. So if you have a finite partially ordered set, a finite poset P, then what you can do is O sub P is the polytope, which is the convex hull of the indicator vectors of upper order ideals of P. So what do I mean when I say this? What I mean is the dimension of your ambient space is the number of elements in P. Each element of P corresponds to one coordinate in R to the D, where D is the number of elements of P. And so what I can do is for each upper order ideal, I can just take the 0, 1 vector that tells me which elements are in the upper order ideal. All right. And it turns out that there's a lot of information about the partially ordered set that is contained in the geometric and arithmetic structure of these order polytopes. And so one thing I want to point out is these are really combinatorially defined. It's like, I've got a finite post set, I've got this combinatorial set of upper order ideals, and I encode them as indicator vectors, take the convex hull, and now I'm in geometry land. So a second example attached to a finite simple graph G are symmetric edge polytopes. So what you do with these is P sub G is the convex hull of E sub I minus E sub J and its negative for each edge ij in the edge set. And so it's an edge polytope because the edges of G control which points of the vertices, and it's symmetric because you're taking the positive and the negative, right? So this is a centrally symmetric polytope. And symmetric edge polytopes, they are of interest for a lot of different reasons. You know, one place these came up was like independently arose was because they model the normalized volume of these things, model aspects of solution, number of solutions and solution spaces for certain systems of differential equations, the Kuromoto model of differential equations. So, but again, I have a combinatorial object with graphs. The edges just encode the vertices, and then the convex hull gives me geometry. And then finally, I have matroid base polytopes. If you know what a matroid is, then you know the matroid base polytope P of M is the convex hull of the indicator vectors for the basis sets of M. Yes, for an order polytope in response to the chat, the number of vertices is equal to the number of upper order ideals. That's right. And matroid base polytopes are useful in optimization. Okay. All right, so this is a bunch of examples. Some come more from algebra, some come more from number theory, some come from combinatorics. There's a huge number of lattice polytopes. Right? And one important theorem, this holds in general, not just for lattice polytopes, but for all polytopes, is that every polytope can be described as the intersection of finitely many closed half spaces. And that's called the H description. All right. So polytopes have a V description and they have an H description, and these contain equivalent information. And just to give a few examples of this, the standard simplices, which we saw were the convex hull of the standard basis vectors in the origin, those are the set of all x's where the entries are non-negative and the sum of the entries is less than or equal to 1. So this gives you D plus 1 half spaces. Okay, 1 for each coordinate plus this one. The minus 1, 1 cube, there's supposed to be a 1 there. The minus 1, 1 cube is the set of all x's where each coordinate is greater than or equal to 1 and each coordinate is less than or equal to 1. So there are 2D closed half spaces that define this. And for order polytopes, for a poset, how do you define this? Well, you take all the x's, all the vectors x, where each coordinate is greater than or equal to 0. Each coordinate is less than or equal to 1. So that's size of p many inequalities for the 0, size of p many inequalities for the 1. And then you throw in some more inequalities. You have xi less than or equal to xj whenever I is less than j in your poset, or less than or equal to j, I should say. So again, you'll notice here that for order polytopes, the vertex description is combinatorial in terms of the upper order ideals, and the half space description is combinatorial in terms of the relations. This happens quite often. Okay. And so the thing that I don't want to give you the impression of is I don't want to give you the impression that somehow the half space descriptions are always really nice. So let me show you one more of these. Okay. So this is a theorem from 2018 due to Higashitani, Yohemko, and Machalik about symmetric edge polytopes. So you take a finite graph and you take plus minus EI minus EJ for each edge. So for these things, you can think of the half space, the closed half space, defining one of the intersection half spaces as being taking the inner product with some function f on the vertex set with your vectors x and setting that less than or equal to 1. There's a theorem for these objects that says you can always take like f dot x less than or equal to 1 for certain integer functions f on the vertices. Okay, so what are they? Well, there's two conditions on these normal vectors to your closed half spaces. The first is that for any edge E equals UV, the absolute value of the difference between U and V in F has to be at most 1. So as you're moving through the graph crossing edges, either you have the same value or it goes up or down by 1. And the second thing is that the subset of edges E sub F, where the difference is 1, has to form a spanning connected subgraph of G. So for example, if you want to try to understand the structure of the half plane description for these symmetric edge polytopes, you have to first understand all of the spanning connected subgraphs of G. And then for each of those spanning connected subgraphs, you have to look and ask, is there an integer labeling of the vertices that satisfies this condition that in absolute value, I differ by at most 1 from one vertex to the next that's adjacent. So that's not a straightforward thing to do. All right. And I see there's a question. Can any of the other examples be described as ordered polytopes of some P? Let's see. Not necessarily exactly as I've described them. If you do a unimodular transformation, the standard simplices are the order polytope of a chain. So, and the 0, 1 cube is the order polytope of an anti-chain. So the -1, 1 cube is not. But off the top of my head, I don't think any of the others can. Okay. All right, so let's just make a few comments here. So now that we've seen V and H descriptions and we've seen some examples, what are some notes? First note is that converting from the V description to H description and vice versa is very non-trivial. And this is just copy paste from the CRC handbook on discrete and computational geometry. There's a chapter by Seidel. And I just want to read to you, very briefly some of what he writes at the very beginning, which is the quote unquote convex hull problem is a catch-all phrase for computing various descriptions of a polytope that's either specified as a convex hull of a finite point set in R to the D or as the intersection of a finite number of half spaces. And then, the very first thing past the introduction is the phrase computing the convex hull is a phrase whose meaning varies with the context. Consequently, there's been confusion regarding the applicability and efficiency of various convex hull algorithms. So whenever somebody talks about oh, just compute the convex hull, actually what they mean by that can differ in different contexts. All right. And so I just want to toss that out there because I definitely have noticed this. If you're talking to an enumerative combinatorialist versus somebody who's really a discrete geometry studying lattice polytopes versus an optimization person versus whatever, sometimes they'll just talk about oh, you just compute the thing, and what they mean really is different. Okay. All right. So a second note is that many, but not all, lattice polytopes of combinatorial interest, if you're like an enumerative combinatorialist or something, are obtained as the convex hull of a set of vectors where each vector has coordinates 0, 1, and -1. So again, if you have combinatorial objects that are finite, it's very common to represent those those things as via an indicator function for a set or a subset, or via some kind of signed sum. And so it is quite common that you will see 0, 1 and 0, 1, -1 polytopes show up in combinatorial problems. But third note is that many interesting questions that are about general lattice polytopes, not restricted to kind of this class of 0, 1, -1 polytopes, are actually of a lot of importance in these combinatorial contexts as well. So it's good to kind of get a sense, if you're a combinatorialist, of like, what is it that the lattice polytope people, the just pure lattice polytope discrete geometry people, what are they interested in? Because these questions definitely have lots of very fascinating special cases in combinatorial contexts. Okay. Maybe before I'll go on, I'll just stop and say, are there any questions at this point that haven't been put in the chat? No. All right, cool. Any corrections in the spirit of the seminar that Matthias said? So anything I've said that's incorrect that an expert would like to say, you're wrong. All right, cool. Okay, so let's talk about just some guiding questions, right? Like, what are some guiding questions that we should have in mind whenever we are thinking about lattice polytopes? I would argue that probably the most important guiding question is, given a lattice polytope P, what is the volume of P? Computing the volume of a polytope is something that just shows up all over the place in lots of different reasons. Like I said, in combinatorics, you get really nice formulas. In applied mathematics, normalized volumes will bound the number of solutions to certain systems. It just shows up everywhere. All right. In algebraic geometry, volume has implications for a variety of things. Okay. Okay. So one thing I want to mention for lattice polytopes, it's typical to normalize the volume. So the volume of the standard simplex is 1. So this lattice triangle here, the standard simplex in R2, in Euclidean volume, that's got volume area 1/2, but from a lattice point perspective, its volume is 1. One thing that does is every lattice polytope has an integer normalized volume. Okay, and that makes this work out. For example, this theorem that I guess is due to Stanley from back in the 70s says that for an order polytope P, the volume of the order polytope is the number of linear extensions. And so, so you should think, if you know anything about computing number of linear extensions, that's a very hard problem. And so computing the volume of polytopes is at least as hard as computing linear extensions, and it is hard. Okay. All right. So the question is, how do you actually compute the volume, right? And so one thing is, you can quickly compute volumes for lattice simplices for a simplex. Again, a simplex is the convex hull of d+1 points in R to the d, and it's d-dimensional. Okay, so it's like the smallest number, generalized triangle and tetrahedron, right? For lattice simplices, we can reduce to a certain normal form called Hermite normal form, which is an upper triangular presentation of the simplex. That's just by these unimodular, lattice preserving transformations. And when we do that, then we can quickly get the volume. All right. So one approach, a very typical approach to computing the volume, is to subdivide the polytope into simplices and then add up all of the volumes, right? Add up the volumes of all the simplices. So that leads to a second big guiding question, which is, how can we subdivide lattice polytopes into simplices? And the kind of most common subdivision, the one that we all want to think about, is a subdivision of a lattice polytope that's a simplicial complex is called a triangulation. And for lattice polytopes, these should be lattice simplices. Okay. So in other words, you take a lattice polytope, you take all the lattice points inside, boundary and interior, and try to break the thing into lattice simplices in a way that the resulting triangulation is a simplicial complex. Okay. That's a triangulation. And so here are some pictures. I took these from the book by De La Guerra, Rambos, and Santos called Triangulations. If you're interested in this topic, I strongly recommend that you look at that book. It's got a lot of good stuff in there. So I'm going to start in the middle here. So if you have a pentagon, you just have a, whether it's a lattice pentagon or otherwise, if it's a lattice pentagon with only the lattice points as the vertices, there are 5 triangulations, right? And those triangulations basically all look the same combinatorially because they all consist of 2 edges emanating from some vertex, but obviously the labels change. Now, if you had a hexagon, suppose you had a hexagon where the corner vertices were lattice points, but nothing else inside the polytope was a lattice point. Then you would have these different triangulations, okay? Or sometimes you might be interested in restricting your triangulations to only building the simplices out of the vertices, for example. That's okay too. And there's actually a structure called flips on triangulations that let you kind of move from one triangulation to the next. And that leads to the whole theory of secondary polytopes and a whole lot of other stuff. But what I really just want to, the reason I wanted to put this picture down is just so you can get a sense that even for a 2-dimensional polytope, kind of getting all the triangulations written down and figuring out how to walk among them in some reasonable way is not totally straightforward. There's some interesting structure is what I mean. And then here on the left, if you take an icosahedron, this is not a lattice polytope, but if you take this polytope, you can break it up into simplices, add up all the individual volumes of the simplices, that'll give you the total volume of the polytope. So this is the idea, okay? So one question that you might have is, well, can we always triangulate a polytope? And the answer is yes, polytopes always admit triangulations. One construction that's a very standard way to prove that every polytope admits a triangulation is to use what are called liftings, and those yield regular triangulations. So just for example, if you imagine that you've got some, this is probably not realistic from a lattice point perspective, but just pretend, again, this picture is from the triangulations book. Pretend that you had some quadrilateral, right? Where the corners were lattice points and then you had 3 other lattice points inside. Then what you would do is you would take R2, you would embed that quadrilateral in R2, then you would add a 3rd dimension. And for each of the lattice points, you would lift it up to some height in that 3rd dimension. So you're viewing the polytope that you're interested in, which is d-dimensional, as kind of a shadow of a d+1 dimensional lift of the polytope. And so when you lift up all those points, you can take the convex hull of the lifted point configuration. Then you take kind of the bottom faces and push them down. And as long as everything is generically lifted, what'll be pushed down will be a triangulation. The chambers that result will be simplices, okay? And one thing to notice is like this lattice point in the middle that my cursor's on, it was lifted much higher than the others. And so it's not really involved in this lower envelope. So for this triangulation, that lattice point is not a vertex, right? It's kind of not involved as the vertex of one of the triangles, right? So it's, I won't say it's completely straightforward, but it's, it is a standard exercise to show that if you that you can always generically lift the vertices or the lattice points of a polytope in such a way that when you take the convex hull and then project the bottom part back down, the lower hull back down, you get a triangulation. Okay. All right. So triangulations exist. And if triangulations exist, then, hold on. Yeah, Jeremy. So Jeremy asked, what does regular mean in this context? Regular means that it's the projection of a lifting. I don't know if there's some deeper meaning to the word regular in that case, but that's like the defining quality is you do a lifting, take the convex hull, project the lower envelope. And if you lift it in a non-generic way, so maybe like these 2 faces here, like I'll draw a little line on these 2 faces, if those 2 faces, when you lifted it, if they were a quadrilateral instead of 2 triangles and you projected it back down, then you'd get a quadrilateral. And that's a subdivision, but it's not a triangulation. And that's still called a regular subdivision. Any subdivision that comes from a lifting is regular. All right. Okay, so so one thing that would be nice in the lattice polytope case would be if I could skip the whole compute the volume of the simplex thing. So in other words, if I have a lattice polytope, if I can find a triangulation where every simplex in the triangulation is unimodular, or is a standard simplex, sorry, is a standard simplex, or is unimodularly equivalent to a standard simplex, then there's no volumes to compute. Each volume is one, and I just add them up. And the number of simplices in the triangulation is the volume of the lattice polytope. That's actually what happens with those order polytopes, is that there's a canonical triangulation of the order polytope that gives a triangulation into simplices, each of which is a unimodularly equivalent to a standard simplex. And so you get the volume is the number of linear extensions, because there's a bijection between simplices in the triangulation and linear extensions of the poset. So that's kind of like the gold standard for like a really well-behaved lattice polytope is going to be one where you can break it into unimodular simplices, right? Every simplex has volume one. And so a triangulation of a lattice polytope is unimodular if that holds, if every simplex has volume one. And it's important to note that this is in the purple below, not every lattice polytope has a unimodular triangulation. And so kind of the standard example of this is the Reeve tetrahedron. In R3, you take the convex hull of the origin, the first standard basis vector, the second standard basis vector, and the vector 1, 1, 2. So this has 4 lattice points. The only lattice points in this tetrahedron are the vertices. There's no others on the boundary or in the interior, and its volume is 2. So a unimodular. Okay, so sorry, I'm back in the chat again. So a unimodular simplex is a simplex that is unimodularly equivalent to the standard simplex. What that means is there is some affine lattice preserving transformation that takes the standard simplex to this other simplex. So that's what it means to have a unimodular simplex. And then a triangulation is unimodular if every simplex in the triangulation is equivalent by an affine lattice preserving map to the standard simplex. Does that make sense? Hopefully that makes sense.
So here, does this transformation preserve the volume?
Yes. Yeah. If you have a lattice, so the lattice preserving transformations are the elements that are in GLN or GLD, okay, but they have to have integer entries, and the determinant has to be plus or minus 1.
I see.
So if you take like the semi-direct product of GLD Z with translations by integer vectors, that gives you this whole unimodular, affine unimodular.
Okay, thank you.
Yep.
Second question.
Yeah.
If kind of what it means to have volume 1 is you can be translated into the simplex, what does it mean to not have a unimodular translation but still have volume 2? Like, where does this notion of this is exactly double, not one volume?
Yeah, so this is the weird thing that happens with lattice polytopes, right? It's all about the arithmetic. I mean, so if you think about it, like where does this Reeve tetrahedron come from, right? Where it comes from is you basically have like the unit square in R2, and you take like the infinite prism over it, if you like, right? And then what I do is I take, the origin, and I take E1 and E2. And if I wanted something that would be standard, like a unimodular transformation of a standard simplex, I would take the lattice point that's at 1, 1, 1, right? That would just be a skew transformation of the standard simplex. Instead, I go up to height 2. I take 1, 1, 2. And you can see that because I'm in this very thin vertical chamber, right, that there's no other lattice points in sight on the boundary or inside the polytope. And so just arithmetically, what you've done is you've found 4 lattice points that the convex hull, it's an empty lattice polytope, meaning that it doesn't have any lattice points on the boundary or inside it other than the vertices. and it happens to have volume 2. And you cannot transform that with a lattice preserving transformation back to the standard simplex. It won't fit.
Right. My question is, what does it mean to have volume 2? Because for me, volume 1 means.
Yeah, it means that in this case, if you compute the Euclidean volume, so the normalized volume of P is going to be d factorial times the Euclidean volume of P.
Okay.
Now, the problem is that if you're in a situation where you're like, if you're a line segment in R4 or something, then what you have to do is you have to take the affine span of that line segment, and then you look for a minimal lattice simplex in that line segment and define that to have volume 1. And that then normalizes what the volume computation is. Yeah. Okay, good.
Thank you.
Yep, no problem. Other questions? It's great.
Correct me if I'm wrong. So a geometric, the geometric volume of a tetrahedron is like 1/6, and you can't fit 6 of them in a cube, right? So is it something
Yeah,
similar
you can
happening here?
for the standard simplex. You can fit. Yeah, if you take a cube. Hold on. Again, let me draw a picture right here. If you take a cube. And if you, so let's imagine that like this right here is the origin, and this right here is the all ones vector. Okay. Try that again. So the origin is on the far side. The all ones vector is up here on top. All right. Then what I can do is I can cut this cube with the hyperplanes x1 equals x2, x2 equals x3, and x1 equals x3. That's called the type A braid arrangement. And when you do that, what will happen is that you'll end up cutting this polytope into 6 chambers, and each of those chambers is equivalent to by some unimodular transformation is equivalent to a standard simplex. So if you were to kind of look at it, if you were to line up the all ones vector and the 0 vector and look at them kind of straight on top of each other, you would see, oh, then let me try that again.
Right.
You would see this picture. And each of these triangles is just like a tetrahedra projected down. So,
Right.
Yep.
Oh.
Okay. Cool. All right. So basically, what you should kind of get out of this is that triangulations are not straightforward. Okay. And if you want to know more about unimodular triangulations, which are again these like really nice ones, there's this AMS Memoirs volume published in 2021 by a number of other people, by Hassa, Pfaffenholz, Piechnik, and Santos, and it's very up to date. So they've got a large amount of really good stuff in there. It's kind of a mix of a survey article and new results. Okay, so getting kind of actually to Mark's question, which is like, how can you have these simplices that are like the Ron volume, but they don't have any extra lattice points in them? That's actually a good guiding question, right? Like, are there lots of simplices like the Reeve tetrahedron that are empty but not unimodular? So empty simplices means that you have the d+1 lattice points that are the vertices are the only lattice points in the polytope, interior or boundary. And the answer is yes, there are a lot of them. And it is an open problem to classify them. So the classification of 3-dimensional empty lattice simplices was done in the 60s by White. And the 4-dimensional classification was just published last year. And so this description right here tells you what it looks like. There's a 3-parameter family, there's 2 2-parameter families, 46 1-parameter families, and then there's 2,461 exceptional cases. And so 4-dimensional simplices, like if you ask like, if I triangulate a 4-dimensional lattice polytope, what simplices might I see once I've really broken it down as far as I can and I can't subdivide it anymore? The answer is you're going to see one of these 4 types, including, 1, 2, 49 infinite families, and then these roughly 2,500 exceptional cases. Okay. So it gets really wild is the point. All right, so one thing I do want to point out is that this idea of classification problems is kind of just another general guiding question for lattice polytopes, right? And they're related to like enumeration and finiteness problems. So, so let me give you one example of this. A lattice polytope is reflexive if that lattice polytope, so being a lattice polytope means you're the convex hull of a bunch of integer vectors. You're reflexive if your half-plane description has the following structure. It's the set of all x's in R to the d, where ax is less than or equal to the all ones vector for an integer matrix A, meaning that every half space looks like an integer vector dot x less than or equal to 1. Okay. This is equivalent to the statement, if you know about duality, that the geometric dual of P is also a lattice polytope. So these reflexive polytopes come in pairs. All right. And I already showed you that the -1, 1 cube and the cross polytope are a reflexive dual pair. And actually, there's another example that we've seen, which is the symmetric edge polytopes. Those are also known to be reflexive. These are, this is, I should say, it's a very fascinating class of polytopes. I've thought a lot about these things. I think back in 2006, when I was in my last year at grad school, I gave a talk about reflexive polytopes at Kansas when Jeremy invited me. So, we're just continuing the dialogue from way back when. But one important theorem about reflexives is that for a fixed dimension, there's only finitely many reflexive polytopes. And that's a corollary of a theorem due to Hensley back in the 80s or 90s, I think in the 90s. And Kreutzer and Skarka, who are two mathematical physicists, they actually computed these numbers exactly for n equals 2, 3, and 4. And so the number of reflexive lattice polytopes is 16 in dimension 2, 4319 in dimension 3, and a hair under half a billion in, a hair under, half a billion in 4 dimensions. For n is greater than or equal to 5, nobody knows, and it's probably not feasible to actually compute this number. But hey, that's cool.
And if I could ask, are all those known polytopes, I don't want to see that source code, by the way. Is there any symmetry within each of those groups? Or are each of those 4,319 pairs sui generis?
Yeah, so there are some that are self-dual, their duals are unimodularly equivalent to themselves. So some of them are not actual pairs.
Okay.
And
this is polytopes, not pairs.
Yeah, this is
got
polytopes.
it. Okay.
Yeah, and so there are various ways. So again, the physicists, these things, reflexive polytopes originated in the work of Batarev and Borisov studying string theory, these Calabi-Yau hypersurface pairings, and so which I don't really understand, but they have a whole lot of interesting invariants that they attach regarding Hodge theory and other things to these. So
I was just thinking that
filter through the family.
I was just thinking that, if you classify triangulations of an n-gon, we know there are catalog many of them, but they come in. There are a lot of equivalence classes up to symmetry of dihedral group or something. Where is there a similar group action that classifies these into orbits of a group action or something? Yeah,
so maybe 10 years ago or something, I forget exactly. There was a paper by Ben Nill and some others about the graph of reflexive polytopes. They have this construction of a way to connect reflexive polytopes by an edge if they're related by some operation. And then they were interested in trying to kind of study this graph to see how you could generate examples and stuff. So
which might not be connected.
Yeah, but so it's not, the reflexive polytopes are have this beautiful definition, and there's these really lovely special examples, But then if you actually go into the wild with them, just like, oh, just give me a reflexive polytope, they just get really crazy, you know? So, I mean, so if you're like, I like graphs, there's a bunch of reflexive polytopes attached to graphs, and like, we can talk about those. They're still really hard to understand, but like, we can talk about those. If you're like, I like reflexive polytopes, then all of a sudden you're like, oh man, there's just this unimaginably large, complicated, you know.
They're all sort of their own idiosyncratic things, probably.
Yeah, exactly.
Okay.
So, yeah, I mean, even just understanding reflexive simplices, you know, there is a classification, but the classification is, here's an algorithm that will classify them all. That's exactly what this classification is too. And so if you actually somehow want to understand them all, quote unquote, at once, it becomes much more difficult. So,
Thanks.
Yep. Okay, so here's another finiteness result. Again, I'm trying to emphasize that lattice polytopes have kind of this nice enumerative flavor. So there's a theorem, this is in the 90s from Ligarius and Ziegler, that there's only finitely many lattice polytopes of a fixed dimension and bounded volume. So if you fix a volume K and you say, how many lattice polytopes are there of dimension D and volume less than or equal to K, there's a finite list. And there was actually a really nice proof of this recently. I think it was published a year or two ago by Belletti, that is like a very accessible, just purely linear algebraic discrete geometry proof that it's really lovely. But again, you kind of get this notion that like, if you put a few mild restrictions, then the number of lattice polytopes suddenly, it's a giant world, but it's finite. And so that's kind of this idea that lattice polytopes are much more restricted than general polytopes. Okay. All right, and so I'm close to ending time. So I'm gonna actually skip some of this that I was gonna say, and I'm gonna go back to volume and just kind of return to this question of how do we actually compute volume like algorithmically, all right? And there's a couple of related questions. One is, how do we compute the Hilbert basis for the cone over P? That's an arithmetic structure attached to P. And the other is, how do we compute the Ehrhart polynomial for P? I've thought a lot about Ehrhart theory, and you know, both these questions are very closely related to the volume question. And one answer to computing volume is algorithmically is to use Brion's theorem and what are called Barvanock decompositions. And this was really it's kind of a major avenue that was used by the people who developed Latte and the people who developed software called Barvanock. And the idea of Barvanock decompositions is that if you want to understand a particular cone, like this cone on top in blue, then you write this cone as a signed sum of other cones. So you can get this light blue cone by taking the whole orthant here in purple, subtracting off this little teal thing, and then adding on a little bit more. And these pictures are from this paper by De Loera in Journal of Symbolic Computation. And the idea is that this cone right here is actually arithmetically complicated, because if you look at the ray generators 2, 7, and 1, 0, the determinant in absolute value is 7. But for each of these 3 cones, the determinant is 1. And so arithmetically, they're unimodular cones. They're much simpler. So there's this whole theory of like signed decompositions of cones, which corresponds to signed decompositions of polytopes, and lets you kind of compute in this way. Another answer is to use what are called pyramid decompositions and lexicographic triangulations. So this is described very nicely in this 2016 paper by Bruns, Ickerman, Söger on the power of pyramid decomposition and Normalize. Normalize is software that Bruns has been developing with colleagues for many years to compute all these different invariants of lattice polytopes. And so what pyramid decomposition looks like is, and this will be kind of the last thing I say in the talk. Good, okay, good time. Is that one way to build a triangulation is to do what's called a Lex or placing triangulation. So for example, if you look at these 7 points here in the upper left, then what I can do is I can start with point 1 and I connect point 2 to point 1. Then I take point 3 and I ask, what can I see previously? I can only see point 2, so I connect 3 to 2. Then I take point 4. Point 4 over here can see the whole line segment of length 2. So I make 2 triangles by like coning over that. Point 5 is up here. it can only see this face. So I add that. 0.6 is right here. It sees this whole face of length, or this face, triangulated face of length 2. So I cone over that, etc. And similarly in R3, if I kind of took this tetrahedron, I tossed this point on, which is in this quadrilateral plane, but I would get this triangulation. And then if I coned over that, I'd see like 3 more tetrahedra tacked on. And what a pyramid decomposition does is it ignores the triangulation that's happened so far, and it only does the facets. So at this step right here, when you're right here, in this picture, what they're doing, right, is they actually cone over the triangulation. So you get 2 triangles. But in a pyramid decomposition, you cone over the whole facet and you get a non-unimodular triangle there. And similarly, in this picture, this is actually a quadrilateral. So in the pyramid decomposition, when you tack this point on, you're actually coning over the quadrilateral. And so you run that whole process, and what you end up with is a triangulation where some of the simplices in the triangulation are not minimal volume. So you take those, and then you run the same operation on those using the same relative ordering of the vertices. And these Lex triangulations like line up properly on the boundaries. So what this allows you to do is you get kind of this first pass that might not even be a simplicial complex, because like here I've got like the cone over a quadrilateral. But then I just take that polytope and I run the same algorithm on it, and you can run the different chambers in parallel. So it lets you do a lot of parallel processing. This then develops this triangulation very quickly, right? And this is kind of the whole idea of how you get to volume and how you get to Hilbert bases and Earhart polynomials and other things in Normalize, is this very clever like parallel processing decomposition technique with pyramid decompositions. It's very simple, but like extremely interesting, and like it's kind of amazing that it wasn't done before they implemented it. You know, it's like a natural thing to do, but you know, somebody had to do it first. So anyway, so yeah, so I'll just leave you with you know, a few more questions without commentary. One is, how can we prove a regular triangulation is unimodular? There are techniques. How do I construct new lattice polytopes from old ones? There's a bunch of techniques. How do I sample a typical collection of lattice polytopes? There's recent Markov chain Monte Carlo algorithms and ways to generate things from random graphs. So, so there's a whole lot of these kind of guiding questions that lead to really interesting math. So, all right, so I'll stop there. Thank you very much for coming, and yeah, thanks for having me.
All right, thank you, Ben. Let's thank our speaker for the excellent talk. If Ben has time, we can have some questions.
I've got about 4 or 5 minutes, and then I've got to run off for.
All right. All right. So if you have quick questions, please ask away.
Hello. Hi. I
Hello.
have a quick question. Could you explain briefly what in this context, what the Hilbert basis is?
Yeah, sure. So if you take, let me bring up this picture quickly. Need the cone. All right. So what you can do is for any lattice polytope, any polytope at all, but in this case for a lattice polytope, you can take the cone over P. So what you do is you take P and you embed it in RD plus 1 at height 1. So just append the coordinate 1 to every point in P. So for example, this quadrilateral gets embedded in R3 at height 1 on the z-axis. And then you take the real non-negative span of all the points in that lifted polytope. And that gives you what's called the cone over P. And the object of interest here for a lattice polytope is you want to look at all of the integer points in that cone. And so that forms an additive semigroup. It's an affine semigroup, and it has a unique minimal generating set. So like over the integers, for real non-negative integers, there's a set of integer points in this cone that will generate all the other integers through non-negative integer combinations, all the other lattice points. And that minimal additive generating set is the Hilbert basis. So.
Well, if there are no other questions, I might make a comment.
Yeah.
So just as one of the pathological things that happens in polytope land is that, of course, if you start with a polytope that doesn't have integer vertices, but it has rational vertices, then you can just dilate it, multiply it by the right amount and get a lattice polytope. And of course, you can compare the volumes. But starting in 4 dimensions, there are combinatorial types of polytopes that can't be realized just with rational vertices. So
yeah, it's that those scare me. So I really like integers. Sometimes my friends and students will push me into rational world, and so quotients of I see Andres is here. Hi, Andres. So sometimes they're like, we got to do something rational, and I'm like, all right, fine. But even the rational numbers scare me a little bit. So.
I'll mention that if the polytope is not integer, then the Ehrhart polynomial has non-constant coefficients. The coefficients are periodic, but in your case with the lattice polytope, when you have a lattice polytope, the Ehrhart pseudo quasi polynomial is actually a polynomial.
Yeah.
So there's a genuine algebraic combinatorial phenomenon that distinguishes rational from integer.
Yeah, and one of the interesting questions still about that is there are some rational polytopes that have no period, that have period 1, where it's a genuine polynomial. It's this period collapse for quasi polynomials, and I think that's still not fully understood.
I was about to ask if that could happen.
Yeah. Terrell McAllister has a number of papers on this, and there's some like scissors congruence type approaches to this, but I haven't heard of any big resolutions of some of those types of questions recently.
Do you know a small example offhand of such a polytope? I can go look at
No.
papers. I'm just curious.
Yeah, there are lots of examples just of rational triangles in the plane. There are examples.
Okay.
Yeah, Andres might know, but I don't know off the top.
I don't think it happens in dimension 1, but
no, but in dimension 2 already, it's a kind of weird phenomenon. I must admit, I have no real understanding of it. So.
Ben Wormlington at Washington University in St. Louis has thought about this stuff a little bit, based off Alex Kasprzyk's stuff, but it's very algebraic. And you know me, so I try to stay away from the algebra, but it keeps on coming in, so it might be worth revisiting.
Cool.
Very arithmetic, I would think.
Yeah, it's really arithmetic.
Yeah.
Anyway, hey,
Right,
I gotta scoot out of here.
Yeah.
But it was really good to see everybody, and
Thank you.
Thanks again for the
thank Ben again.
invitation. So.